Hello my dear students, I hope you are enjoying this series on vector calculus. So in this video we are talking about a very important concept, so that is torsion for a given curve. So what we saw till now, you have some curve which is x of t, right? We saw that at any point we can have a tangent vector which is defined as x prime t upon mod of x prime t. Then we defined a normal vector which is defined as t prime t upon norm of t prime t, and then we saw there is a binormal vector which is defined as t cross n. Okay, and we also saw that dt by ds is equal to kappa times n, and this kappa was the curvature, and that was telling you the rate of change of the angular angular rate of change of the curve with respect to the parameter s. That means how fast your curve is turning, right? Okay, so now we have another result which tells us dB by ds. This result we have already proved, this one, right? But the result which I am citing right now, this is equal to minus tau times n vector. Okay, so these two results look similar. Can you see? This is the derivative of t with respect to s, and this is the derivative of b with respect to s. B is our binormal vector. So this is equal to minus tau times n. So we have to see what is this minus tau. So we'll prove it later in the maybe next 2-3 videos. We are going to prove it later. But we are going to define tau. Tau is torsion of a curve. It measures how sharply it is, turning out of the osculating plane. So torsion of a curve tells us torsion at a point, right? If you are calculating torsion at a point, it tells us how sharply the curve is turning out of the osculating plane. How sharply the curve is turning out of the osculating plane. I told you in the last video what is osculating plane. This was a kissing plane. So if I have this curve at this point, right, I want to know that there is a t vector and there is a n vector. So this is my plane, osculating plane. So I want to know how fast this curve is moving out of that plane. So basically this torsion quantity tells us that how three-dimensional your curve is. How three-dimensional your curve is. So for example, if you have a two-dimensional curve, suppose I have a parabola. If I ask you what is the torsion of this curve, that is going to be 0, because this parabola is never going to come out of the paper plane, right? So it's not a three-dimensional curve, so torsion will be 0. So torsion basically tells you that how fast, how sharply your curve is getting out of a plane, right? So how three-dimensional your curve is. For example, suppose you have a curve like this, which is very slowly coming to the next plane. Maybe this was z is equal to 0 plane, and this is in z is equal to 0.1 plane. Then you have a curve which is, here it was in z is equal to 0 plane, and then here it is in z is equal to 100 plane, right? So this is coming out sharply from the osculating plane here. So this has more torsion as compared to this curve, right? So do you understand what is the meaning of torsion and how do we calculate it? We write dB by ds as minus tau times n. So that is your torsion, right? Okay, so we can also say that because this n is unit normal vector, so we can say dV by ds modulus is going to be tau. Tau is a constant quantity, like scalar quantity, right? So basically this also will give you the torsion, right? So we'll be doing some problems, and before that I would like to tell you that curvature is always positive by convention. Curvature is always positive, and this tau can be positive, 0 or negative. Okay, this can be always greater than equal to 0. Curvature can also be 0, right? We saw for a straight line it is 0. So this can be positive 0 or negative, your torsion, right? So in this video I am just doing two problems where we will be calculating the curvature and torsion. That's it, right? Okay, so let us look at the first problem. First problem is simple. We have our circular curve a cos t, a sin t. This is my path, circular path. So I have a particle moving in a circular path. Particle moving in a circular path, right? So now if I want to calculate my curvature and torsion, so for that we have our tangent vector, that will be x prime t upon mod of x prime t. So that would be minus a sin t comma a cos t divided by a square sin square t plus a square cos square t. So that is equal to minus sin t. This is minus a sin t, a cos t, and if you look in the denominator here, this is a square comes out and you have sin square plus cos square. Sin square plus cos square is 1, so you have square root of a square, that is a. So this will be minus sin t comma cos t, right? So therefore you get your tangent vector to be minus sin t I cap plus cos t j cap. So this is your tangent vector. Now if I want to calculate my normal vector, that is going to be tangent vector divided by derivative of tangent vector divided by its mod. So derivative of tangent vector is cos t I cap minus sin t j cap divided by its magnitude, that would be cos square t plus sin square t. So that would be minus cos t I cap minus sin t j cap. So this is our normal vector. And then we can go for the binormal vector, that would be t cross n. So you have your t vector here, you take the cross product with this, so that would be I j k. So if your t vector is minus sin t cos t I cap 0, there is no k component. Here it is minus cos t minus sin t 0, and if I do the calculations, I'll get k times sin square t plus cos square t, sin square t plus cos square t, because for I cap there is a 0 row, so you'll get 0. For j cap also you'll get a 0, only k cap is having a non-zero component, right? Therefore you get that bt is a constant vector which is unit k vector, right? So if I try to do dv by ds, that is going to be 0. So I know that dv by ds is minus torsion time n vector is 0. So that means torsion has to be a 0 quantity, and that we expect also, because you are saying that your curve here is a circular curve, so your particle is moving in a circle, so it is not coming out of the plane, right? So there is no torsion in this particular curve. So we'll do one more problem. So till now we were just doing circle or helix, so I'll give you a little complex problem so that you can work on it yourself. So you can start with xt equal to e raised power t cos t comma e raised power t sin t comma e raised power t. Look at this curve and your okay, let us try this thing. So I give you 10 minutes. Okay, so you take 10 minutes. It will take approximately 10 minutes to solve this problem and solve this problem. Find its curvature and torsion, right? And then in the 10 minutes, after 10 minutes, if you're done with this problem, or maybe you can take 15-20 minutes if you are, it depends on how you're doing it, then you can see the next video and find out your solution. Thank you for watching this video. Please share this video and subscribe to this channel. Happy learning.